Next up, we have Robert Steenburgh from NOAA's Space Weather Prediction Centre, who's going to tell us what it's like to be a space weather forecaster and what space weather forecasters are looking for and why it's important.
Hello, my name's Rob Steenburgh. I'm a scientist and forecaster here at the Space Weather Prediction Center in Boulder, Colorado. We forecast space weather for a variety of reasons. It started out in the really in the 40s because we used high-frequency radio communications to talk over large parts of the Earth, and we needed to understand what the ionosphere was doing in order to do that effectively. And the ionosphere is influenced by the sun, and so beginning to understand that helped us with propagation. From there, as technologies move forward, our level of technological dependence continues to increase, and space weather has a huge impact on technology, in particular things like satellites and spacecraft, humans in space, all the way down to the ground here on Earth, where you have impacts on the electric power grid, for instance, on aircraft communications, things like that, and all the way to seeing the aurora. A lot of people are interested in being able to see the aurora. So it's a collaboration between research, operations, between government and commercial. So we forecast space weather as a way of alerting different communities of potential impacts to their systems and to making sure people are safe and that we can deal with the impacts so that we're prepared. One piece of information we'd love to know is what that magnetic configuration is as it leaves the sun, and really being able to watch it evolve as it moves towards Earth, because that's the determining piece, one of the determining pieces of the strength of the magnetic storm. It's a key piece of information. We don't have that until the thing's at our doorstep. So on the sun, we look for the sunspots. The sunspots that grow, become more complex and big, typically produce flares. So the flares are here in 8 minutes, affecting our ionosphere. You see a degradation of HF communications on the sunlit side of the Earth. Sometimes those flares can also produce energetic particles, proton events. So you can see those arrive anywhere from minutes, or typically minutes to hours. Those present a problem for the astronauts because they are considered radiation workers. They're up in space. We're protected here by our atmosphere and our magnetosphere, but they're kind of closer to the action. And that puts them at risk. And the primary hazard that they face when they're up there is an increased cancer risk based on that ionizing radiation. And then finally, you can get these huge eruptions, these coronal mass ejections that come off as well. There are images of the sun called coronagraph images. Those coronagraph images are key. We can use the coronagraph to see, for instance, a coronal mass ejection come off the sun. With the coronal mass ejection, you have a big tearing off of a blob of plasma that is explosively ejected from the sun. And we can say, okay, looks like it might be Earth-directed. This is when we have to prepare for geomagnetic storms. And we have, depending on the speed, from about 18 hours or so to 3 or 4 days. We see it in the coronagraph briefly, enough to get a handle on its speed. And then we don't see it anymore. And it's like a ghost moving through space. And it doesn't show up again until it hits a spacecraft that we have 1/100th of the distance from the Earth to the sun, and it hits that spacecraft, and that's the first time we actually understand what the magnetic field inside that cloud looks like. Those carry with them an embedded magnetic field. When they travel to Earth in hours to days, and they impact our magnetosphere, that can cause geomagnetic storming. Once it gets to Earth, so the magnetic field, if it's oriented correctly, sticks to Earth's magnetic field, starts ripping the field lines off as it passes over, and that violence leads to the fluctuating magnetic field and the geomagnetic storm. And then what's going on with the aurora, you've got particles that are injected into the poles. They interact with our atmosphere, and that interaction causes the glowing that you get from the aurora. And depending on the level of geomagnetic storming you have, it can push that aurora down to lower latitudes. In fact, in 1859, during the Carrington event, they got aurora down in places like Cuba, it was bright enough here in Colorado that miners got up to go to work thinking it was dawn, and really it was still nighttime. It can affect the ionosphere, so you can have communications problems. It can affect GPS, so you can have GPS issues. So those are some of the impacts we look for as well. Induced current on power lines, impacts to spacecraft, space station, risk to human health. Another thing that can occur is these energetic particles I mentioned earlier get trapped on our magnetic field lines and routed into the auroral regions. And that can wipe out communications over the poles for days. It's an event called D-region absorption. And when that happens, airlines have to reroute their flights to avoid that no communications area. And in doing so, burns up a lot of fuel. There's another type of feature that causes geomagnetic storming on a less severe level, and those are the coronal holes, these areas of the sun that are open, and they appear black, big dark regions. You can see them in X-rays, and you can see them in extreme ultraviolet. And those regions have high-speed solar wind emanating from them. When they come around, they can give us some geomagnetic storming and pump up the electron levels. The different space weather effects that we see, and trying to ascertain what they came from, that's an important part of our job. Important part of the process is trying to determine, okay, we're seeing this particular impact on Earth. What can we ascribe that to? And generally, we can link, we have an understanding of flare does this, particles do this, geomag storm does this. So we can see and look for those kind of impacts. So I think the way we tell where the impacts come from is by mapping it back to a particular phenomena that we observed, whether it was a flare or a particle event or a geomagnetic storm caused by a coronal mass ejection. So yeah, that's kind of how we go from impact back to origin. Usually we're working in the other direction though. We're observing an event and going forward to warn people that they could see impacts from an event. Operationally, we have to make decisions to send out warnings and alerts and watches before the graph is filled in. We get the line up to here, and we have to know or try to figure out what the rest of the graph is going to look like. What we're looking at here is a prototype of an electric field model, or E-field model, that will be able to depict in near real time the electric field over the continental US. This is important for power company operators because geomagnetic storms can induce current on power lines, and that induced current can in turn damage the transmission system, damage transformers if it becomes too large. This particular event we're looking at occurred in 1989, so this is a historical revisiting of the storm. And this storm caused a power outage in Quebec that spread down into the northeastern US. And it was significant in that it left a lot of people in the dark. As a meteorologist, I never really thought about the sun much other than, yep, it's in the sky. How hot is it going to make Earth today? Oh, it's where it's supposed to be setting in the evening. All right, we're good. That's about the level of thought than I gave to that particular thing. And it was amazing to learn how much was actually going on. And so we can walk around day to day, mostly not think of it, but when it does throw off something significant, it'll get your attention. And so that's what we're here to keep an eye on it. Differences between space weather and terrestrial forecasting boil down to a lack of observations in the space environment with the same density that we have in the terrestrial environment. We're swimming in data. In meteorological terms, it's kind of like you see a wave off the coast of Africa heading across the Atlantic, and you go, hey, that wave, that easterly wave might develop into something. Could be a hurricane. And then you don't get to see anything else until you get the phone call from Cuba, and the guy's like, ah! And it's kind of late now because it's in Cuba already. And that's kind of what it's like for us. If you think about the space era, we haven't been looking at the space environment with vehicles in space for a very long time. So this relatively short time scale, we haven't seen all the events that could happen. So it's kind of like if you think in terms of terrestrial meteorology, what's a 100-year flood, and that's something that the scientists are now grappling with, beginning with the documentation we do have of events and kind of working through that and through the science to understand how bad a magnetic storm could be, how big could a flare be, and what would be the impacts then on the systems. The eclipse, I think the thing that'll be fun about that from my perspective is we're going to see, we should be able to see what it does to the ionosphere, because that ionization, the UV and X-ray emissions from the sun that give us that ionosphere, they're going to be turned off in this swath. So it would be interesting to see what kind of impact that has. Is it discernible? Is it something we can measure? Should people be worried about the space weather? I would say they should be aware of it. But if you think about it, how long have we been on Earth? A really long time. And you're not outside on a daily basis going, protons. Nobody does that, it's not like hailstones, In fact, most people don't even know it's happening most of the time. It's an amazing time to be a space weather forecaster and a scientist in this field. It's just absolutely amazing because we're learning more all the time, but there's still ways to go to hone our ability to forecast space weather to get us to a place, if we can get there, to a place where we're on par with what we can do currently with terrestrial weather. We're learning more. I think that the work that's being done in the research community and the recognition of the importance of the impacts of space weather and being prepared for space weather is all very encouraging. And I hope we can kind of continue that momentum. We need observatories in space and on the ground. We need research from the most basic understanding levels all the way through to the applied levels here. And part of our focus has been really trying to bridge that chasm sometimes between research and operations and weave these things together. That's an important thing, and it's awesome to be part of that. I mean, it's really an awesome job.
Thanks for that, Rob. It's fascinating to see how the different areas of solar physics play a big role in our understanding of the sun and how it affects the Earth. We really hope that you enjoyed our webcast this month and are starting to realise how all of these different pieces come together in the single field of solar physics. As we get ever closer to the total solar eclipse, it's a great time to get in touch with us with your questions. If you have any questions about content that we've already covered or anything that you would like to see us cover, please get in touch. You can email us at outreach@nso.edu. You can find us on Facebook at www.facebook.com/National Solar Observatory. On Twitter, our Twitter handle is @NatSolarObs, and on Instagram, we're @National Solar Observatory. Don't forget to subscribe so as you get notifications of upcoming webcasts, and we look forward to seeing you again next month.